Hi, my name is Sune Schung Jebsen, and I'm a PhD student at the University of Southern Denmark Software Engineering section. I will present our paper, An Analysis of Asset Interoperability for I4 Middleware. Industry 4.0 is characterized by linking machines, products, and processes together into an intelligent network. The interoperability of systems becomes important, supporting communication flow between machines, and hence our motivation to analyze asset interoperability for I4 middleware. The middleware is the software that glues the enterprise application and control application on the production floor together. And the figure illustrates all the various interfaces connected to the middleware, facilitating communication flow for a production sequence. An asset is anything that needs to be connected to create an I4 solution, for example, machines, sensors, or software. And we will focus on the interoperability between the middleware and the machine software. The asset interoperability analysis for I4 middleware is based on the level on conceptual interoperability model and our experience from our Industry 4.0 lab. Our question is, can the levels of conceptual interoperability model be used to analyze different assets interoperability levels related to I4 middleware? To answer the proposed question, the following steps are taken. An ontology is presented which forms the basic semantic knowledge model for concepts and their relationships within the manufacturing domain. And the ontology is used to illustrate interoperability levels in the LCIM. And next, the LCIM is mapped to the communication between the middleware and the assets, together with examples illustrating the semantics for each level, and lastly, a discussion of the mapping follows. Instead of developing a new ontology, we took the approach using an existing ontology named the Mason ontology within the manufacturing domain, which gives us core concepts and the relations. The modeling is based on automated warehouse and a collaborative transport robot, also known as an AGV, automated guided vehicle, from prior experiences in our lab, capturing the abstraction of machine capability seen from a middleware perspective. Based on the Mason concept, machine resource operation and logistic operation, we modeled the automated storage. Looking at the T-box, the terminology box, we extended with new concepts. A storage is a machine resource. A storage contains raw material. It enables realization of a program, and the program executes placing and picking logistic operations. The A-box, assertion box, illustrates instances of the T-box, in this case, the warehouse 1 from our lab. The core abstraction is the notion of a program which enables us to invoke behavior on a resource based on capabilities. To the right, the ontology structure is shown in a simplified JSON structure, indicating two available programs for either pick or place operation. The context lets us refer back to which ontology describing the concepts and the relation for storage. And here we model a collaborative transport robot, the AGV. A resource is composed of multiple resources. For example, a resource is composed of both a mobile transport and a cobot, where the cobot is a multi-axis robot. At the A-box, we create an instance of the mobile robot composed of the AGV and a robot arm, which enable realization of a program with pick, place, and transport capabilities. Currently, the program executes a sequence of operation, pick, place, and transport, and the ontology will be used to explain the levels of the LCIM in the upcoming slide. So our analysis of the LCIM. Level 0. Assets which fall into this category are not intended to operate in an I4 environment. Level 1. Assets has the ability to produce and consume data over an agreed communication protocol. And level 2. Assets share a common data format. For example, assets are able to produce and consume JSON. Level 3. Addresses the problem of having different vendors with different models and concepts, and the hassle of having humans in the loop to understand and map data. Having a meta model describing the data gives us a shared understanding of concepts and relations in context. For example, the storage has picking and placing capabilities, as do the mobile robot, but in a different context of their use. And level 4 addresses a common workflow of how to use the data. Let's say the warehouse picks an item from storage faster than expected, and the mobile transport is still busy. Would it then be possible to pick another idle mobile transport? The pragmatic level is a step towards being able to handle such uncertainties based on abstract knowledge models. And level 5, here we know the effect of data being able to do better qualified decision, meaning that if I know the effect of choosing another mobile transport would give lower throughput, then I would rather wait on the planned mobile transport. And lastly, level 6 gives a full understanding of all interoperating systems. From the former example, the system will know that the warehouse will be able to process faster than expected before it started, and from there be able to adjust the production. So our conclusion is that the LCIM illustrates a hierarchical level of interoperability, helping us to grasp the complexity to achieve higher levels of asset interoperability for I4 middleware. And semantic model is a step towards an intelligent I4 network of assets. The ontology is an example of semantic model creating an abstraction between the middleware and the production floor machines. The LCM model may seem rather intuitive, but the reason that we see this as an important topic within the I4 domain is because too many assets fall into category 0 and 1. Robotic and automated solution has had many advancements in the field of the last many years. Being really good at what they do, now it's time to be good working together, forming an intelligent network of machines and processes. Thank you for listening.